All right, guys, any questions before we start? Okay, we'll do a few problems. So this problem says scouts at a camp shake the rope bridge they have just crossed and observe the wave crests to be 8 meters apart. So 8 meters is roughly from here to the wall. Yeah. So this is the rope bridge, and that is the wavelength, which is 8 meters. Okay. If they shake the bridge twice per second, so they're shaking it twice per second, so the frequency is 2 hertz. Hertz is 1 over second. Okay. And of course, it's named after Mr. Hertz. Yeah. So what is the propagation speed? What is the velocity of the wave? Is just frequency times wavelength. Okay. 8 meters times 2, 16 meters per second. Yeah. So what is the wavelength of an earthquake that shakes you with a frequency of 10 hertz and gets to another city 84 kilometers away in 12 seconds? So velocity is frequency times wavelength. So wavelength is velocity divided by frequency. And the velocity of the wave is 84 kilometers. 84,000 meters divided by 12 seconds. It took 12 seconds to get there. Okay, so this is 7 meters, 7,000 meters per second, 7 kilometers per second. Okay, and so you will learn when you earthquake waves. So earthquake are waves traveling through the earth, and the earth is solid, and solids can, what kind of waves can travel through solids? I'm sorry? Both transverse and longitudinal waves can travel through, okay? And these waves happen to be longitudinal waves. Okay? Transverse wave travel about 4 kilometers a second. Okay, these are also called primary waves or P waves. So now the wavelength is V over F, which is 700 meters. So the wavelength of this wave is 700 meters. 700 meters is roughly from here to nowhere. Okay? That's the wavelength of the wave. Okay, this problem says your ear is capable of differentiating sounds that arrive at each ear just 0.34 milliseconds apart. Okay. So for instance, why do you have 2 ears?
So you can determine a position of what
Yes, so localization. Okay, so for instance, if a sound is coming from the left, it reaches this ear first, and then it reaches the other ear. Okay, so because it's delayed, this computer can figure out that the sound is coming from the left. All right, the sound coming from here reaches at the same time, and sound coming from the back also reaches at the same time. but that is coming from the back has to go through your head. Okay. And anyway, so it uses all that kind of information to localize sound. Okay. So your ear is capable of differentiating sounds that arrive at each ear just 0.34 milliseconds apart, which is useful in determining where low frequency sound is originating from. Suppose a low frequency sound source is placed to the right of a person whose ears are approximately 18 centimeters apart. So that's 18 centimeters. And the speed of sound generated is 340 meters per second. How long is the interval between the sounds arriving at the right ear and the sound arriving at the left ear? Okay, so here's the, okay, so sound gets here first, and then it gets to that ear, and this distance is 18 centimeters, okay? So T2 minus T1, the time difference is the speed of sound times this distance divided by time. The distance it has to travel divided by the speed of sound. Yeah. By the way, so it's coming here and I'm having the sound travel through the air. If it had to travel through your head, what is your head?
Solid.
Salt water. Okay. So you would have to use the speed of sound in salt water. Okay. Through your body, it's mostly salt water. Okay. So you're using this. Okay. 18 centimeters, which is 0.18 meters, divided by 340 meters per second. That's 0.53 milliseconds. Okay, so that's enough of a delay for this computer to tell that this sound came first and this sound came later. If this delay was 0.2 milliseconds, this computer won't be able to tell which sound came first. Okay. All right, let's increase this speed. Let's increase the speed. If you increase that speed, what would happen? The time difference would decrease. That's what happens underwater. Underwater, the speed of sound is 5 times greater. This time difference would be 5 times less. It would be 0.13 seconds. Let's say 0.1 second. Then this computer can't tell which sound came first. So if you're underwater, you can't tell which direction the sound is coming from. And that's what happens to the manatees. Well, they're slow swimmers, but they can't tell where the sound is coming from. So how long? Okay. Assume the same person was scuba diving at a low frequency sound source was to the right of the scuba diver. The speed of sound in water is 1500 meters per second, 5 times that. Okay, so you can't tell which way the sound is coming from. Okay. So this problem says a pulse can be described as a single wave disturbance that moves through a medium. Consider the pulse defined at time t equal to 0 seconds by this thing. Okay. So if you plot this pulse, it will look something like that. Okay. So for x equal to 0, it would be 6/2, 3. So 1, 2, 3. So this pulse is something like this. Yeah, that's how it looks. Y x equal to 6 over x squared plus 2. Okay. You want the pulse moves with a velocity of 3 meters per second in the positive x direction. So you want this to move at 3 meters per second. Okay. So what will be the pulse? So how do you describe that pulse? Which would be x minus 3t squared plus 2. Yeah. X minus vt. Okay. What is the amplitude of the pulse? So the amplitude of the pulse is, this is the amplitude of the pulse. The amplitude of the pulse is y0. Well, you saw that at x equal to 0. The amplitude of the pulse is 3 meters. Where is the pulse centered at time t equal to 5 seconds? At t equal to 5 seconds, it's centered at 15 meters. Okay. All right, we'll do this one problem and then we'll be done. What is this?
It's a wave moving to the right with a that is phase shifted.
Yeah. So it's a sine wave moving to the right. Sine and cosine waves are the same, okay? Moving to the right. All right. So what this is about is we want to identify all quantities. That's the amplitude of the wave, that's the wave number, that's the angular frequency, that's the phase shift. Okay? And so our wave is given by 0.25 meters, 0.25 meters, 25 centimeters. That's the amplitude of the wave. So you can think of, it's probably an ocean wave or a wave on a river. 0.3x, and I'm not writing units, t plus pi by 3. Okay, here's how you remember the units. The phase, what are the dimensions of this guy?
Radians?
Yeah, dimensionless, radians, okay. Okay, so this is in meters, so this has to be inverse meters. This is in seconds, so this has to be inverse seconds. And this is in radians, dimensionless, okay? So what you want to remember is the argument of cosines, logarithms, exponents, they're all dimensionless, okay? All right. All right, so this is the amplitude, this is the wave number, angular frequency, okay? So the amplitude is 0.25 meters. Wave number k is 0.3. What are the units? I'm sorry? Inverse meters. Okay. C, angular frequency, 0.9, inverse seconds. Okay. Wave speed, what is wave speed? Omega by k, 0.9 3 meters per second. E, what is the phase shift? pi by 3. And f, the wavelength is k is 2 pi by lambda. So lambda is 2 pi by k. Frequency is 1 over period. Okay, so period Okay, so the point of this problem was the following. Oops. This little function contains a whole bunch of information about the wave. Okay, it contains all the information you need to know about the wave. It has the amplitude, wave number, angular frequency, velocity, phase shift, period, and all that stuff. Okay. All right, guys. All right, we'll stop here.